Tonight, our speaker is Robin Anthony-Petersen, and Robin grew up in the Bay Area playing frisbee and camping. She attended Lane Community College, intending to major in math, but instead found her home in the collaborative space of experimental physics. To finish her undergraduate degree, she transferred to UCLA as a physics major and then started grad school at UC Berkeley in 2021. At Berkeley, she works at the Space Sciences Lab on gamma ray telescope called COSI, which we'll be talking all about today. So please, Robin, take it away.
Thanks, Daniel. Okay, hi Rudy. Thank you so much for coming out tonight, especially all the people who've known me since I was little. It means a lot for you to be here. So yeah, I'm going to be talking about gamma ray astronomy, what gamma ray astronomy is, why I think it's really exciting, and this telescope I work on that I think is going to change how we do gamma ray astronomy. And if you have any questions during this talk, please feel free to ask at any time. The more questions you ask, the more I get a sense of how well I'm doing up here. So I appreciate questions. So I'm going to start off by looking at the version of the night sky that we would all see if we went out to a dark sky region and looked up. So this is the optical sky. It's made by looking at particles of light, which we call photons, that have energies that our eyes can detect. And this is the view of the night sky that astronomy has historically been built on. We are able to look at a lot of things in the sky. So this is the galactic center, and then we have the galactic plane. So you can imagine that we're looking at our Milky Way galaxy through the disk. And so that means that where Earth is in this perspective is where we're sitting, and Earth is looking out at the Milky Way galaxy. And we can study things like stars in this energy range. We can look at planets, and then we can also look at things like nebula. These are big gas clouds where stars are born. You can look at dwarf galaxies. This is the small and large Magellanic Clouds. They're two dwarf galaxies that orbit the Milky Way. And then all of these darker regions in the sky are actually hydrogen gas. So it's absorbing light, and we can map out gas in the Milky Way. So this is, the view of the night sky that astronomy was built on. And because it's the energy range that photons we can see with our eyes emit at, we call this sky the visible sky. But the universe is emitting photons across a really huge range of energies. And the entire range of energies that we know photons can emit across, we call the electromagnetic spectrum. And so on the left, at the really low energies, we have radio waves and microwaves. And then in the middle, in this very small region, we have the visible light that we can see. And then at high energies, you have the highest energy photons created in the universe, and we call those gamma rays. And so today, we are going to leave behind the optical sky, and we're going to go and explore the gamma ray sky. And the gamma ray sky is really interesting for physics and astronomy because to make these high energy photons, you have to have really, really high energy extreme events. And by detecting these photons, we're able to study those events and learn about what's happening. So this is a view of the high energy gamma ray sky as seen by a telescope called Fermilab. And you can see it has a lot of similarities to the optical sky. You can see the galactic plane, and then it's brighter in the galactic center. And these photons are about 1 billion times the energy of the photons we see with our eyes. And some of the things that create these photons are supernova. So when you have a big star that collapses on itself, it's going to explode and accelerate these really high energy photons across the universe, and we can see them. So there are lots of supernova remnants hiding in the galactic plane that we can see with gamma ray astronomy. There are also pulsars. Pulsars are neutron stars that are spinning really fast, and they have these huge magnetic fields. And because of their big magnetic fields, they can also make gamma rays. And then something that's different from the optical sky is we also see all of these really bright red dots that are not in the galactic plane. And these are active galactic nuclei, which are black holes at the center of galaxies that are actively taking in mass. And as they do that, they make a lot of gamma rays, and we can see them. So all of these bright points that are not in the galactic plane are actually extra, not within our galaxy. They're other galaxies out in the universe. So this view of the gamma ray sky is great, and it's great for a lot of reasons. One, because we can actually resolve it pretty well. We have good angular resolution in this range, and we can pinpoint specific point sources, and we can see structural features. So we can do a lot of science here because we can understand what's happening because we can see it well. The But this story changes a lot if we go to the low energy gamma ray sky. So this is a map of what the low energy gamma ray sky looks like right now. And you can see it's very different from the optical sky and the high energy gamma ray sky. We can kind of make out what the galactic plane is, but we can't see any individual sources anymore. And this is because our telescope technology is not very good at this energy range. But there's a lot of really interesting science here, so we need better telescopes so that we can explore this space. So I'm going to talk a little bit about like why is it so hard to see gamma rays here, and if you have any questions, please stop me. But basically, these gamma rays are really high energy, so they pass through material really easily. And if we're trying to detect a gamma ray, what we need to do is take that gamma ray, which is a photon, and turn it into an electrical signal that we can read out with a computer. And we can only do that if we can build a detector that can completely contain all that information of that photon and then turn it into an electrical signal. But because they're so high energy, they just pass through most material and we can't even like get any information about them. So that makes it really challenging. In addition to the fact that they can pass through material easily, they also just like don't interact very much. So we have this like double thing where it's hard to stop them completely, and on top of that, they don't interact with matter. Another thing that makes detecting gamma rays hard in this energy range is that not only are they being emitted in the universe, they are also emitted in our own instruments. And this happens when you have really high energy charged particles like protons or electrons that come and hit like the metal around our telescope, and they actually excite the atoms in the metal in the telescope, and they start vibrating. And then to release the energy that they get from vibrating, they emit another gamma ray. And so what I'm showing here in this cartoon is we have like two sources out in the universe that we want to look at, and they're emitting gamma rays in these green wiggly lines. And then we have this high energy electron or proton that comes in and hits our telescope, excites the material in the telescope, and then to de-excite itself, that material releases gamma rays, which are drawn in orange here. And it's really hard for us to tell the difference between those gamma rays in green and the gamma rays in orange. And so this just makes it even harder to like see what kind of sources are out in this space. So these are two of the reasons that it's really hard to have better maps in this energy band. So the question is, since these gamma rays are hard to see, should we just leave them alone? And I would argue absolutely not, because there's a lot of really, really interesting science that's happening in this energy range. And I mean, part of the reason that's hard to see is because there's so many things emitting here too. So not only is our instrument emitting gamma rays, there's just so many things in the universe emitting gamma rays, and then they're hard to detect well. So all of these things are just compounding to making this one of the least explored regions in the entire sky. And so as an experimentalist, I think this is really exciting because we have a huge opportunity to figure out how we build better detectors so that we can go and explore this part of the sky. So before we talk about the instrument I work on, I'm going to talk about two questions that I think we could answer with better telescopes to look at this region of the sky. And since I have a physics background, these are slightly more physics-y type topics. But the first one I'm going to talk about is called the positron problem, or positron puzzle. So this has to do with antimatter, so I'm going to start by explaining what antimatter is. So if we have our electrons are particles that are around us all the time. We interact with them every day because they are responsible for all our electric currents. If you don't have a favorite particle yet, electrons should be your favorite particle. They're definitely mine. And the electron has an antiparticle out there, and we call it the anti-electron or positron. And this particle is basically the exact same as an electron on the quantum level, except that it has positive charge. So like the mass is the same, the way it interacts with gravity is the same, but their charges are different. And just like electrons are all around us, positrons are actually around us too, just in a much smaller quantity. So an example is bananas actually make positrons. They make about one positron every 75 minutes. And yeah, so positrons are just around us. Like we interact with them in the lab all the time. They're really common. I think sometimes when we think of antimatter, we think it's like this big crazy thing that's like super hard to make. But yeah, positrons are bouncing around. Yeah.
Why does the banana make the positron?
Yeah, so it's because of nuclear decays. And I'm actually going to talk about that a little bit more later. And then maybe when I get to that, we can see if I've answered your question. But yeah.
Do we make positrons?
Do we make positrons? If we have elements that are unstable in our body, we do, but I don't think we have any of those. If we eat a banana, though, yeah.
How long do they last?
The positrons?
Yeah.
That's a really great question. Okay, so that takes us to the next slide, actually. How long do positrons last? Well, the thing is, as soon as a positron meets an electron, it is going to annihilate, is what we call it. It's going to destroy itself and the electron. And so as you can imagine, we have lots of electrons everywhere. So this positron that leaves the banana is not going to make it very far before it meets an electron, and then it's going to annihilate. Now the question is, what happens to all the energy and mass that these two particles had when they annihilate? And so for this, we turn to Einstein's equation, E equals mc squared, and we know that mass can be converted into energy. And so this is actually what happens when this positron and electron collide with each other. They're going to turn into two gamma rays. And they turn into two gamma rays because we have to conserve momentum also. So they make two gamma rays, and because this positron and electron have really defined masses, the gamma rays have really defined energies. In fact, each gamma ray has the exact same energy as the mass of the positron and the electron. And this is really exciting because it means that we can look for this energy line anywhere in the universe, and when we see it, we're like, oh, this is probably created by electron and positron meeting each other and annihilating. And so, because these gamma rays are in the exact energy range, this low energy gamma ray sky that I'm interested in, the question is, okay, can we see positron annihilation in this map? And the answer is yes, we can. So here's a plot from real data from a telescope that was looking at the MEV sky. And what we have on the y-axis is number of counts, and it's specifically number of photon counts. And then on the x-axis, you have energy. And in keV, which is a unit of energy, electrons and positrons have a mass of 511 keV. And that's exactly where we see this big spike in number of photons. And so this tells us that we can actually measure by counting this peak, how many photons are created, how many positrons we have in the universe. Now the question comes around where we actually have way more positrons than we would expect from how we know positrons are created. And this has been a mystery for the last 30 years of where are all these positrons being created. So this might hopefully answer your question. So some of the theories we have, one of them is the astronomy's version of how all these positrons are getting created, and it could be happening in supernova. So when you have a supernova, again, it's this big star that's reached the end of its life and it's exploding. And it's made a lot of heavy elements, and not all of those elements are stable. One of those elements that's not stable is aluminum-26. And it's not stable because it actually has more protons in its nucleus than it likes. Protons are positively charged, right? So they're actually pushing against each other. And this pushes that nucleus apart into what we call the decay. And the way it decays is it takes a proton and turns it into a neutron. But we have to conserve charge in physics. So to do that, it also makes a positron. Now this is a process that we understand really well, and this is the exact same thing that's happening in our banana. It's just potassium that's decaying, not aluminum. And so this is, we know this is happening, but based on our understanding of supernova, this shouldn't be happening enough to create all the positrons that we see. And when this decays, it creates this excited state of magnesium, and this magnesium is it's wiggling similarly to the atoms in our telescope, and then to release the energy it creates a gamma ray, and now it's in a stable state. So this is a really cool problem because now we have this mechanism that we know creates a positron, and it also creates a gamma ray at a different energy. So we can go out and we can look for all the gamma rays that are associated with this decay, and we can see if we get enough aluminum in the universe to account for all our extra positrons. And there are a bunch of prominent decay lines that happen in supernova. There's also iron-50 and titanium-44. And they make these gamma rays at different specific energies. And so we can go and count all the gamma rays at those energies and see, okay, now is there enough matter out there to be making all the positrons that we see? And based on our understanding of supernova, like this would change how we see the universe actually, because we think that there shouldn't be, but maybe there is. But we can't tell right now because we don't have a good enough telescope. So that's like how astronomers might try to answer this question. Yeah.
Are you accounting for redshift when you measure the gamma ray frequencies, like the gravity?
So this one doesn't have to.
Oh no, like the normal distribution from the energy measurements that you have.
If you go back to the 511
Yeah.
percent.
Sorry, like this plot, right?
Yeah.
Um,
Or is the redshift just like negligible?
I think the redshift is negligible at these
Okay.
energies. Yeah. Yeah, so the redshift matter is like an optical for sure, but I think when you get down here, like, sorry, this energy is so high. It's, yeah.
Okay, thank you.
Yeah, this is redshift. Okay. Cool. So where we are is astronomers think supernova might answer the positron puzzle, but then physicists have a different idea, and they think that these positrons might be getting created by dark matter. So I'm going to first explain like why we think there is dark matter in the universe and like what it is. So again, if we look at a galaxy, this is like an image of all the visible light and matter that we can see. And this galaxy is rotating, and we know how to define how it's rotating. And so what astronomers did was they said, okay, we can see all the starlight coming from here. How about we just figure out how much mass this galaxy has, and then we use our understanding of how things rotate to figure out like the speed that everything should be moving at. So from this, yeah, you can see you can plot your speed as a function of the distance from the center of the galaxy. And you can figure out how fast stars are moving. And so from doing this from a theoretical perspective, just based on inferring the amount of mass from starlight, you get a curve that looks like this. And then an astronomer named Vera Rubin figured out how to actually measure the speed that these stars are moving at. And this is actually where blue and redshift light comes in. She used the fact that when stars are traveling towards us, their light is blue shifted, and when they're traveling away from us, it's red shifted. This is similar to like when you hear an ambulance go by, it sounds different when it's coming towards you versus when it's going away. And from this, she calculated the speed that the galaxies are actually moving at. And she found a huge discrepancy in what we calculated versus what we measured. And so, yeah.
So for antiparticles, is their mass positive relatively to matter particles or negative?
Its mass is positive, yeah.
They're both positive.
Yeah, so everything about antiparticles and particles is pretty much the same except their charge. Yeah, does that make sense? Okay, great question. Okay. So this led to one of the biggest mysteries that we have in physics today, which is why is our theoretical estimates for how fast stars should be spinning so different from what we actually measure. And so to explain the solution that we came to, I'm going to walk through this equation. So this is how we relate the speed the galaxy is spinning at to the properties of the galaxy that we can measure. So yeah, this is the speed, and we have a discrepancy, right? The speed does not equal the other parts of the equation. So something in here is not what we're expecting. You could argue that we measured the speed wrong, but we've measured the speed many, many times, and we're really sure this is right. So we're going to say, okay, we're pretty sure the speed is correct. This is the gravitational constant. It's a fundamental constant. We use this constant for everything from like our GPS to how we put rockets into space to satellites. It would be pretty incredible if we were able to do all of those things and this number was wrong. So we're going to say that this number is also right. And then we have the radius. This is the distance we're measuring from the center of the galaxy. And again, you could argue that maybe this is wrong, but we're measuring it, and it's pretty like clear that we're doing this correctly at this point. So we're going to say this is right. So this leaves one thing, the mass that we're measuring. And something has to be wrong in this equation, and we think it's the mass. We think we're actually not measuring the mass correctly. And since the speed is higher than we expect, that means the mass has to be higher than we're expecting too. And so another way of saying this is, these are all the things that we know of in the universe that we can see. We can see stars, galaxies, and dust. And for us to get this equation right, this makes up only about 15% of the mass in the universe, and the other 85% of the mass, we've decided to call dark matter. And it's because we have no idea what it is. Since Vera Rubin first discovered this discrepancy in the speed things rotate at versus the speed we thought they should rotate at, we've done a lot to try to understand dark matter, and we have a really good understanding of how it works at like large scale structures. So this is an image of a galaxy simulation, and this is where you take like stars forming and then like things creating galaxies and evolve them in a computer simulation to see like what they'll look like later. And you basically cannot do any simulations that match the data we see without dark matter in the simulations. You also can't explain any of the structures we have in the universe without dark matter. You can't explain how things rotate. You can't explain how galaxies collide with each other. You can't even explain how we got from the Big Bang to where we are right now without dark matter. It's the thing that holds everything in the universe together, but we have no idea what it is. Yeah.
Sorry, maybe I'm dumb. Antimatter is the charges and dark matter is the mass thing, right?
Yeah.
Okay, I see them conflated in media, and at first I was like, I thought we knew what antimatter was.
Yeah, okay, this is a great point. So maybe I didn't make this clear enough. Antimatter is like really well understood, and it's like positrons, things being made from bananas or decays. Every single particle we know of has an antiparticle, but this is not a surprise to us. We understand this very well, but something we don't quite understand is why we have so many positrons in the universe. So that's like the one question that we want to answer. And then the second question is, okay, we also have all of this mass that we can't explain, and we've just called it dark matter because we have no idea what it is. So we just gave it this name. Does that kind of make sense to everybody? Okay, if people aren't following, please ask more questions. Okay, so here we are. We know dark matter holds everything together that we know of, but we have no idea what it is. The silly analogy I made for this is, imagine our universe is a jar, and we know how big the jar is, and we know how heavy the jar is, but we have actually no idea what is in the jar. Like dark matter could be like a really small thing, like imagine like fine kinds of dirt, or it could be huge like rocks. Or it could be something totally different, like they could be like fruits in there or something. We have like really no idea. But the basic question we want to ask first is like, what is the mass of these dark matter particles? Because once we know that, we can start answering a whole bunch of the other questions we have around dark matter. Does that all make sense? Okay, cool. So this is just to illustrate this more. So we're trying to figure out what the mass of individual dark matter particles are. Unfortunately, we have a really, really big mass range to look for dark matter particles. It's about 80 orders of magnitude that we're searching. So we have upper bounds on this. The upper bound is set by these things called primordial black holes, which are a dark matter candidate. They would basically be black holes that were created at the very beginning of the universe, and they're about asteroid size. And we have limits on how big they could be, because if they were bigger, we would have seen them by now with like micro lensing. But we haven't seen them yet, so they must be pretty small. So that sets our upper limit for dark matter, very kindly. And then on the bottom, we know that dark matter holds together structures in our universe. And so the smallest structures we have are things called dwarf galaxies. If you remember in the optical sky, I pointed out the large and small Magellanic Clouds. And so we know that dark matter has to be able to interact with dwarf galaxies, and that sets kind of how small it can be, because when particles are really small, they have like really big wavelengths that spread out. And so we have to make sure that wavelength can be contained within a dwarf galaxy. But other than that, we have like no limits, unfortunately. So one of the things that you can do is say, okay, we know there's dark matter in the galaxy. Let's say it's a particle. What if dark matter, just like matter that we know today, has an antiparticle? And what if when these two particles meet, they annihilate and they create gamma rays? And what if we, on Earth, were able to look for these gamma rays? And just like when a positron and an electron collide, they're going to make gamma rays that are really specific energy. Dark matter would also make gamma rays that are really specific energy. So on Earth, we can make telescopes and we can try to look for this line and see if we can see it anywhere. Another theory, and this ties us back to positrons that we really like, is what if the dark matter annihilated and made these extra positrons that we see? So maybe we understand supernova perfectly. They're making the number of positrons we expect them to make, and it's actually dark matter out there in the universe that's creating these extra positrons. And if that was happening too, then we would see this extra 511 line and we could look for it. So this takes us back to the question of like, okay, we have these two big questions we want to answer in the low energy gamma ray sky, but we don't have a good enough telescope to really try to answer any of them. And the way you could answer the specific question about positrons is if you were able to observe the sky in more detail, you could try to see if there were like specific locations where you see more positrons. And if there are specific locations where you see more positrons, then you can also see if you see more aluminum there. And if you do, then you know if those are coming from supernova would answer that problem. Or if you see positrons coming just from kind of everywhere, like evenly spread out, well, that means they're not coming from just supernova. They're coming from some other processes that are happening. And then we can wonder again, oh, maybe this is dark matter. But again, we need a better telescope. So this takes us to COSI, which is the Compton Spectrometer Imager, and the telescope that I work on here at UC Berkeley. So this is an image of what COSI is going to look like when it's launched. It's going to be a satellite. It's a NASA Small Explorer satellite mission. And telescopes in general are capable of doing three things. They can do spectroscopy, which is where you measure the energy of the particle you're detecting. Then they can do imaging, and that's telling you where in the sky that photon came from. And then they can do something called polarization, which is where they measure this other property that light has about like how it's oriented. So COSI is really cool because it can do all three of these things. When you submit a project to NASA, you also have to tell NASA what exactly your project is going to do and like what questions it's going to answer. And so COSI is going to look at positrons and uncover the origin of galactic positrons. That's our main science goal. Then we're also going to look at these nuclear decay lines from supernova. And then we'll study like extreme environments, like active galactic nuclei and black holes and stuff like that by measuring polarization. And then we're going to contribute to multi-messenger physics, which is where we are using like gravitational waves and also detecting gamma rays and using them together to do science. So the main part of COSI and what's going to set it apart from all other telescopes that have come before it are its detectors. The COSI uses 16 germanium detectors. This is a CAD rendering of them, obviously. And I'm going to talk a little bit about how we decided on germanium. So I work with our detectors a lot, so this is like my favorite part of talking about COSI. We're going to go back to gamma rays are really hard to stop, right, because they have so much energy. So to detect them, we have to have really dense IZ material. Otherwise, they're just going to pass right through, and we don't convert them into an electric signal, and we don't learn anything from it. The next thing is we want to be able to look for these lines that are being created by electron-positron annihilation and also by aluminum or maybe dark matter lines. And so we need what's called really good energy resolution. And this is basically if you have a specific line you're looking for, we need our detector to be really good at giving us back that specific line. If you have a bad detector, it's going to make this line broader, and then it's going to make the counts and the peaks smaller, and so it's harder to see that line compared to other things that is happening. And germanium is the material that has some of the best energy resolution. And then you also need to be able to tell where the gamma ray came from, otherwise you can't do imaging. And so all of these criteria led us to using high purity cross-strip germanium detectors. Germanium is dense. The high purity gives us really good energy resolution, and using cross strips means that we can read out the positions in individual, like, of where the photons come from. Yeah.
Speaking of the energy resolution that you need, and thinking of just say thermal broadening of the line versus inherent spectral non-broadening of the line. From these sources, how much effect is there from thermal broadening of these lines?
Okay, so I think not much, and the reason is thermal stuff happens at a much lower energy than we're talking about. So thermal stuff normally happens at about like, it depends on your environment, but it's like in Kelvin, it's like 10 to the 8 Kelvin. Gamma rays have energies much higher than that by like 2 orders of magnitude if we talk about like black body spectrum. Does that kind of make sense? So you're basically not going to have a big effect for thermal broadening on lines.
So even in a supernova event?
Yes. Yes. Yeah. Okay. Any other questions, or did that make sense? Yeah.
Yeah, I was curious how these detectors differ from the Fermilats and why they're better at detecting lower energy gamma rays.
Okay, great question. So the fundamental difference is that Fermilat detects gamma rays for a very different mechanism than you can use for low energy gamma rays. Do you know the difference between like Compton scattering or pair? Yeah. So Fermilat uses pair prediction, and they use silicon detectors, and you basically are having a gamma ray pass through your silicon detector, and it's pair producing, and you read out all of the charge we get from the pair production. But for our energy range, we can't pair produce. The gamma rays are not high enough energy, and they Compton scatter instead.
I see.
Yeah.
So what's approximately like the resolution on, compared to Fermilats? Because I know like for the lower energy of Fermilats, not that great, but comparatively.
Okay, so our energy resolution is about 1%. 1%, yeah, so it's like between 6 to 10 keV full width half max. Does that make sense?
Yeah.
Yeah, and then the big difference also is Fermilat has really good angular resolution. I think it has like 0.05 second resolution. COSI will not have good energy resolution because we use Compton scattering, so it's going to have about like 2 degrees. So there's like orders of magnitude difference in the angular resolution. Yeah, thanks. Is there another question? Okay, cool. Yeah. Okay, so COSI's detectors are like really novel, and they're going to change how we do gamma ray astronomy, and they're built on a really long history of doing balloon campaigns. So I'm going to give balloon campaigns like a moment to shine because I didn't know about balloon campaigns at undergrad, and I really wish I had. So what a balloon campaign is you have some instrument that you want to put in space, but NASA doesn't know if they trust your technology yet. So they say, okay, go prove that this works before we give you money to actually put it on a rocket and then make it a satellite. And one of the ways you can do this is with balloons. So these are called like high altitude balloons. You launch them normally from Antarctica or New Zealand. And COSI started out as a balloon campaign in about like 2003. And you like build your whole payload, and it's really cool as a grad student because you get to be like really involved in everything. The budget is much smaller, there's a lot less overhead, so you have to like really be hands-on, nitty-gritty, and you take your payload and you like fly it to New Zealand or Antarctica, and then you get to assemble it there and you put it on this balloon, and you normally get to stand there and like do all these launch attempts and so forth. So COSI's had 2 successful balloon launches. The last one was in 2016 where they launched from New Zealand, and this is a photo of them preparing to launch. So this is the balloon. The balloon is going to inflate as it rises, so it gets to about the size of a football stadium. And this is a picture of what the payload looks like as it's getting ready to launch. So you have like all your satellites for your power, and then the detectors are like in the main body. And when it was a balloon, it launched out from New Zealand and then had, I think, 46-day flight where it traveled around, and you have a GPS on it, so you get to track it and collect data. And then it crash landed in South America, and they got to like actually go and like find it, pick it up, and retrieve the detectors. And so from this experiment and collecting all this data, they were able to say, hey, look, NASA, we proved that we can fly these detectors in space, that they work really well, and we were able to get really exciting science. And so basically, from doing this balloon experiment and like a bunch of like paperwork and stuff like that, you get to tell NASA that you're ready to be a satellite. And so that's what they did. And in 2018, we got approved to be a satellite mission. And we're hosted by Berkeley. And everything is actually being built mainly at LBL, Lawrence National Berkeley Labs here. And then up the hill, where I work at the Space Sciences Lab, is where we're assembling our instrument and doing everything. Yeah, so here.
Do you get to choose the flight path of the balloon, or does it kind of just like follow the currents and then like decide on its own?
Great question. No, it completely just goes where the wind takes it.
Oh, okay.
Yeah, it's very whimsical.
Okay.
And I mean, they got really lucky that it actually crash landed on land.
Yeah.
Yeah, and this is another reason they launch from the southern hemisphere often, is because there's less cities to fly over, and you really don't want your balloon accidentally crash landing into a city. The other thing though they can do is if they're like, okay, it's time for this to land, they can like cut the core from the balloon and just drop it wherever. So like, let's say they saw it was going to go land somewhere that had people living, they would probably cut it over the ocean instead. Yeah.
What's the mass of the actual instrument?
Of the satellite, I know the mass of the satellite, it's 330 kilograms.
Okay.
Yeah, I don't know the mass of the balloon. Yeah, was there another question? Yeah.
I assume you use telemetry to get the data down just in case you lose the device?
Yeah, so I don't know for the balloon how it's downlinked, I know for the satellite how it's downlinked. So yes, and then it was really exciting that they were able to recover everything because they also had all the hard drives that they could go collect. So anything they weren't able to like downlink from the balloon, it was still saved on the hard drives. Yeah. Yeah.
And they're building it here?
Yeah, they're building it here. We're building it here, yeah.
Like Grizzly Peak?
Yeah, exactly.
Exactly where all those trucks are?
Yes.
Oh,
Yeah,
I was wondering what that is.
Oh, yeah. So if you don't know where the Space Sciences Lab is,
Yeah.
you have LBL, that's like right up after Berkeley. That one's all fenced off close to the
Yeah.
public. And then up right between Grizzly Peak and like the road from campus, there's like 3 buildings, and it's the Space Sciences Lab. And we build things and we put them in space. Yeah.
What part of it exactly are you working on?
Yeah, great question. So, here. Okay, so I work with our detectors, and right now we've gotten all our detectors. So the way this works is we're using solid state detectors. They're grown in these crystals, and then they get sent to LBL where they get fabricated, and that's basically turning this raw crystal into a cross-strip detector. So they do this thing called photolithography, where they put all these chemicals on it, and they're in a fume hood, and then they do all the etching, and they like etch out all our electric strips. And then they send it up to us at SSL. And so this is what I specifically work on, is this last frame, where we're testing and calibrating our detectors and all our hardware, and then building like all our, like assembling like our hardware and our detectors together, if that makes sense. So yeah, I'll walk through what our setup looks like. This is what we call our short-term test cryostat. And we put our detectors in here. Everything has to be cooled with liquid nitrogen. So we have a liquid nitrogen dewar, and this breaks everything down to 90 Kelvin. We have to do this because there's a lot of thermal noise in our detectors, and because we want such good energy resolution, we basically have to freeze all our atoms in place so that they can't wiggle and cause thermal noise. And then we have our detector, which is housed in here. Here's a CAD image that shows it. You can see it's like strips running horizontally. And then we have to bias everything with high voltage, so we use 1,000 volts across our detectors, and this like drips our signal to each side. These are our electronics boards. We have one on each side, and then we can read out our like what the detector is seeing. And so yeah, these are all setups that I work on. And a big thing we have to do is what we call calibrate our detectors. So this happens for any instrument that's built. You have to understand like when it's reading out things, like what those units are telling you, because they're just telling you stuff in like random electronic units. For example, I work mainly on our energy calibration, and so if we put like a gamma ray source out, and this gamma ray source is emitting gamma rays at a specific energy, this is great because we know what energy the detector is seeing, and then when it reads it out in its electronic units, then we can convert those electronic units to the actual energy. So when we put it in space, then it's detecting gamma rays and we don't know what energy those gamma rays are, we can like read that. So I work a lot on this. And here's an example of another spectra. So this is like the plot I showed where we have the 511 line. So the y-axis is counts, and then that x-axis is energy. And so this source here is a cesium-137 source, and it has a peak at 662 keV, and that's that line that you can see going up. So we can use that to calibrate our detector. And then we can also do imaging with our detector. We joke sometimes that our detectors are like really bad quality, expensive cameras, because this is like its version of what it sees when you have a source pointing at it. We now have gotten to the point where we've calibrated 20 different detectors. So what we have to do is we take, like LBL makes our detectors for us, we bring them up to SSL and we see how good they do. There's a bunch of things we have to run them through. Energy calibration is one of them. We have to see how they handle heat. We have to see what kind of currents they have. in the detector. And then once we've determined if it's a good enough detector, then we can add it to like our final payload. So here's an image that shows our engineering payload model. So if you remember, COSI's going to end up flying 16 detectors total. And here we have a model that's like with 16 detectors in it. And we got this running like a couple months ago, which is really exciting. And here's another cesium spectrum. So this is like all our detectors together, like reading things out. So where we are right now in the COSI mission is we went from this CAD model to now we're assembling our final payload. And so here's an image of us, like we have our stack that we're building. We have one detector placed in there now. And then we finally got all 16 of our detectors that we put in together. So COSI is going to be launched in 2027. We are just finishing like all the electric checks on this final payload. And then we have to calibrate everything. Once we've done calibrating it, we have to take it to Utah where we do thermal testing. So something that's really crazy about space is because there's no atmosphere, there's no air, all your electronics can't cool off naturally, so they can get really hot and catch on fire. So we have to take everything into a vacuum chamber and we test all our electronics to make sure that the cooling mechanisms we have in place work. So we'll be doing that in Utah over the summer. And then we also have to calibrate everything while it's in vacuum too, because being in vacuum might change how our electronics work. So that's our plan for Utah. And then once we're done in Utah, we take our payload and we give it to NASA, and they take it in Maryland and like attach it to our full rocket payload. And then it gets shipped to Cape Canaveral in Florida, and it will get launched in hopefully August 2027 if we do our job well.
So physically, how big is that image?
This image?
Yeah.
It's tiny. It's like this size, yeah. I made it look really big here, but it's not very big, yeah. It's pretty heavy though, but yeah, it's yeah.
If the cooling systems fail and this gets set on fire, I know that you already like calibrated all of these. I don't know how long that takes, but how far would that set you back?
So our detectors are pretty isolated from the electronics, and we also have been testing the electronics in stages. So NASA is like really smart about how they do things, believe it or not, but there's a lot of checks we have to go through. We don't get to just give them like our final payload and like accidentally set it on fire. That would be like really amazing. So yeah, like we have a lot of engineers who've been testing our electronics through everything. So when we get to Utah, we don't expect anything to go like be a problem. If something did happen, it would kind of depend what stage of electronics failed, and it would probably be something pretty far away from the detectors themselves. Yeah. Does that kind of answer the question?
Yeah.
Great. Yeah. Yeah.
So to get those images, what kind of lensing do you use? Obviously not refraction, right?
Mm-hmm.
But pinhole, or do you just computationally gin it up?
Computationally.
Really,
Yeah.
just from planar sensing? Oh.
Yeah, sort of. Maybe I can answer your question at the end because it's a little bit more complicated, and I have slides that can walk us through that. But I don't know that everyone else would be interested. Yeah. Yeah.
So first off, congratulations on having one of the better named satellites of all time.
Thank you.
But,
Some people named it.
Yeah. Like, I understand that like 2003 to 2027 is like a relatively long period. I'm wondering if like there any of the like technological advancements we've had since then has like significantly changed the concept behind COSI, or like some of the key parts of its design.
That's a really great question. So a couple things have changed. The biggest is on the electronic side. So when they flew the balloon, so also the last balloon flew in 2016, and then they were going to have another balloon flight in 2018, but that was canceled because of the pandemic. Sorry, 2020. That makes more sense. So what has changed on the electronic side is we used to use these things called preamps. Have you heard of those? Yeah, they're kind of a circuit board, and they're analog, so they kind of take up a lot of space. And when you are in a balloon, if you remember, the balloon payload was like really big. So having electronics that take up a lot of space is fine. But once you go to a satellite, all your mass and all your volume really, really, really matters. So we have to switch our electronics from being analog electronics to being digital electronics. So we actually work with the Naval Research Institute, which is in Maryland or DC, and they've been designing us new custom like electronics chips that take like the amount of space that we have for a readout from being like, you know, this size to being literally like this size. So that I would say is the biggest change, which has also been a lot of work for us on the calibration side, because when you calibrate your instrument, you're not just trying to understand your detector, you're also trying to understand your electronics. And so this is a really big change in electronics. We're going from preamps, which we can literally write equations for on paper, to digital like circuit boards that are super complicated. And so that's been like a really big difference. Yeah. Other than that, we also, the balloon only had 12 detectors, and we have more money now, so we have 16. Yeah. Yeah.
Well, how confident are you that you're going to detect something, and how long will it take?
Super confident. We will actually be detecting like way too much because we have these really high backgrounds again. So we will definitely be detecting a lot of things. We also will definitely detect the positron electron annihilation line. And I know that because the plot I showed you of what that line looks like was actually from the 2016 COSI balloon flight. And so that balloon was only 46 days.
Yeah.
COSI, the satellite, will be in space for at least 2 years, but probably a lot longer. And so if the balloon was able to see it in 46 days, we will definitely be able to see it.
And how long, you like immediately? Like,
Yeah, great question. Okay, so once it launches, we do like all our checks first to make sure everything turns on. If everything turns on, then we have 6 months, whereas the team, we're just calibrating. So we have like point sources in the sky. Point sources are like things like pulsars, where we know what the energy have. They've been like really well studied. And we're going to look at those and like try to make sure that everything that we know from previous missions is lining up with what we see for our current mission. So we have 6 months to do that before any data becomes public to anyone else. And then after 6 months, then we downlink, I think, 3 or 4 times a day, and all that data is available to like everybody in the community. Yeah, and we'll see lots of things. Yeah, so actually speaking of lots of things, I talked about 2 things that COSI is going to look at. I talked about antimatter with this electron-positron annihilation, and I talked about dark matter. But COSI is an astronomy like telescope, so there are a lot of astronomy things that COSI is going to also be looking at. So one example is kilonova. This is when you have 2 neutron stars that collide with each other, and they release a lot of gamma rays when they do this, so we're going to be able to see if there's a kilonova, we'll be able to detect it. There's also galactic diffuse emission. This is just high energy particles randomly making gamma rays. Some people think this is really interesting. Some people think this is really annoying because it's another like high background for COSI, because they're always just making gamma rays from everywhere. You can look at star forming galaxies. We're going to make some of the first measurements of accreting black holes in this energy range for polarization, so that's really exciting. One of the postdocs I work with, her specialty is black holes. She's particularly excited for that one. We also have gamma ray bursts, which are like these energetic bursts of gamma rays, and there's a lot of science there. Nuclear decay lines, which we mentioned. There are these things called the Fermi bubbles, which maybe you've heard of, but they're these like gamma ray like shapes that extend out around our galaxy, like our galactic plane. And COSI will also be able to study this, so we have people interested in that. Yeah, supernova, pulsars, and so there's a lot of like different sources that emit in this range. I talked about 2 of them, but yeah, COSI has a lot of science it's going to be able to do. Cool. So yeah, so that was my talk. Maybe you have something to say?